Hi everyone, now we will look at case study that use numerical method to perform carbon pinch analysis. So the case study that we will be look at today is a refinery case study. As you can see here, table 1 shows the data for CO2 source, while the table 2 shows data for CO2 demand for the refinery case study. The first step of this numerical method is to calculate the flow rate of CO2 in the flue gas, FCO2, and the flow rate of other gases aside from CO2 in the flue gas, FOG. This can be done with the flue gas flow rate, FT, and the CO2 composition given in the table 1 and table 2 by using the equation given here. For example, the flue gas flow rate of S1 is 300 tons per hour and the CO2 composition is 75%. So for the CO2 for S1 is 300 times 75%, which will equal to 225 tons per hour. As for the flow rate of other gases, FOG for S1 is 300 times 100% minus 75%, which is 25%, will equal to 75 tons per hour. Besides using this equation, we also could get the FOG by minus FT with FCO2. Repeat the calculation for FCO2 and FOG for all the sources and demand. After we obtain FCO2 and FOG for all the source and demand, we will proceed to next step. Now we will start calculate the ratio of other gases to the CO2 gas flow rate, FOG over FCO2, by divide FOG with FCO2. Let's take S1 as example. FOG of S1 is 65 while the FCO2 is 225. So we can obtain the ratio of other gases to CO2 gas flow rate of S1 by divide FOG of S1, which is 75, with FCO2 of S1, which is 225. We will get FOG over FCO2 of S1, which is 0.3333. Repeat the step for all the CO2 source. Table 3 shows the FOG over FCO2 of CO2 source for this case study. The same step goes on CO2 demand of the case study. We will now start calculate FOG over FCO2 of CO2 demand of the case study. Let's take D1 as example. We could obtain the ratio of other gases to CO2 gas flow rate of D1 by divide FOG of D1 with FCO2 of D1, which is 0.5 over 49.5. Then we could obtain the FOG over FCO2 of D1, which is 0.0101. Same, repeat the step for all the CO2 demand. Table 4 shows the FOG over FCO2 of CO2 demand for this case study. For the step 3, we will now start calculate the number of FOG over FCO2 level and by sum up the total number of carbon demand with the total number of carbon source and minus with the number of duplicate ratio. Table 3 and Table 4 shows the FOG over FCO2 of CO2 source and demand for this case study, which we just calculated previously. As you can see, there are totally 6 carbon source and 4 carbon demand. So the NS for this case is 6, while the ND is 4. Noted that the FOG over FCO2 of S5 and D4 is repeated. Both of their FOG over FCO2 is 9. Therefore, the number of duplicate ratio NDP for this case is 1, since there are only one repeated ratio. We can now start calculate the number of FOG over FCO2 level, and by using the formula N equal to ND plus NS, minus NDP, which will end up with N equal to 4 plus 6 minus 1 equal to 9, which means the total number of FOG over FCO2 level in the carbon cascade table will be 9. Now we will start construct carbon cascade table. Firstly, we will arrange all the FOG over FCO2 that we obtained previously without repeated in column 1 of the carbon cascade table as shown in the slide. Noted that the total number of FOG over FCO2 in column 1 should be same with the number of FOG over FCO2 level N that we calculate previously. Next, at the column 2, we will start calculate the difference of FOG over FCO2 level for the FOG over FCO2 level from column 1. For example, the value at column 2 that is clouded with red color is obtained by calculate the difference of FOG over FCO2 level from column 1, which is clouded with green and blue. As you can see, we can obtain the value of 2.5 by minus 9 from 11.5. Repeat the step for all other FOG over FCO2 level. The carbon cascade table in the slide shows the result after finish the calculation for column 2. Now, at column 3, we will fill in the flow rate of carbon source at the corresponding FOG over FCO2 interval. For better understanding, let's take the value of 9 from FOG over FCO2 level at column 1 as an example. Refer back to the CO2 source table. We can observe that the FOG over FCO2 level of 9 is come from S5 and the FCO2 of S5 is 20. Therefore, we will fill in 20 at the column 3 as the flow rate of carbon source for the FOG over FCO2 level of 9. Noted that the value of the flow rate for the carbon source is fixed at positive. For the column 4, similar with column 3, but this time we will fill in the flow rate for carbon demand at the corresponding FOG over FCO2 interval. However, different with column 3, the flow rate of carbon demand that we fill in column 4 is fixed at negative. Same, let's take the value of 9 from FOG over FCO2 level at column 1 again as an example. Refer back to the CO2 demand table. We can observe that the FOG over FCO2 level of D4 is also 9 and the FCO2 of D4 is 22. Therefore, we will fill in 22 in negative, which is negative 22 at column 4 as the flow rate of carbon demand for FOG over FCO2 level of 9. Now we will start calculate the net interval carbon flow rate by sum up the flow rate of carbon source and demand at corresponding FOG over FCO2 interval from column 3 and 4. Let's take the same example again. For the value of 9 from FOG over FCO2 level, the net interval carbon flow rate is 20 plus minus 22 equal to negative 2. Repeat the calculation for all the FOG over FCO2 level. The carbon cascade table in the slide shows the result after finish the calculation for column 5. For the next step, we will start calculating the carbon flow rate balance FC by cascading downward the net interval carbon flow rate from column 5, starting from FCO2 equal to 0. For example, the value of 9.51, which is clouded with red color, is obtained by sum up the value that clouded with green color. 2.31 with 7.2, which is clouded with blue color. The carbon cascade table in the slide shows the result after finish the calculation for column 6. Next, at the column 7, we will start calculate FOG surplus or deficit by multiply FC from column 6 with the difference of FOG over FCO2 level from column 2. For better understanding, let's take one of the calculation steps of column 7 as an example. By multiplying the 1.667, which clouded with green color, and the 4.31 that clouded with blue color, we could obtain the FOG surplus of 7.1833 that clouded with red color in the slide. The carbon cascade table in the slide shows the result after finish the calculation for column 7. For the next step, we will start calculate cumulative FOG at column 8 by cascading downward of FOG from column 7 starting from 0. Let's take one of the calculation steps of column 8 as an example. The value of negative 177.4833, which clouded with red color, is obtained by sum up the value before it at column 8, which is negative 158.6667 that clouded with green color with FOG from column 7, which is negative 18.8167 that clouded with blue color. The carbon cascade table in the slide shows the result after finish cascading for the column 8. Next, we will start calculate pure carbon cascade at column 9 by dividing cumulative FOG from column 8 with FOG over FCO2 interval from column 1. For better understanding, let's take one of the calculation steps of column 9 as an example. We could obtain the value of negative 24.2023 in column 9, which clouded with red color, by dividing negative 177.4833 that is clouded with blue color with its FOG over FCO2 interval 7.3333, which clouded with green color in the slide. The carbon cascade table in the slide shows the result after finish the calculation for column 9. As you can see, there is negative value at column 9, which means there are deficit on the pure carbon cascade. This indicates that the pure carbon cascade is invisible. Therefore, in order to ensure that there is sufficient fresh carbon at all points in the network, we will have to supply the absolute value of the largest negative number on column 9 at the highest FOG over FCO2 level at column 10. In this case, the largest negative number on column 9 is negative 89.66, which is clouded with purple color in the slide. Therefore, we will supply 89.77 at the highest FOG over FCO2 level, which is purple color in column 10. This value is then cascaded again with the net interval carbon flow rate from column 5 to yield the visible carbon cascade. For better understanding, let's take one of the calculation steps as an example. The value of 78.37 from column 10, which clouded with red color, is obtained by sum of the value before it at column 10, which is 67.87 that clouded with green color with net interval carbon flow rate from column 5, which is negative 18.8167 that clouded with blue color. The carbon cascade table in the slide shows the result after finish cascading for column 10. Lastly, we could obtain the minimum fresh carbon target, FFC, the location of pinch point, and the minimum carbon emission flow rate target, FCE, from the carbon cascade table. The minimum carbon target, FFC, is obtained from the absolute value of the largest negative in column 9, which is clouded with red color in the column 10. The location with the largest negative number at column 9 also represents the pinch point of the carbon cascade table. The minimum carbon emission flow rate target, FCE, is obtained from the last value of FCE in column 10, which is 99.17 in this case. That's all for the case study for carbon pinch analysis using numerical method. And thank you for listening this lesson.